All right, so we're moving right along into chapter 4, which is all about vector spaces and subspaces. The content in this chapter is pretty conceptually challenging, so I want to just take some time at the beginning here to just spark your memory on what it means to be a vector space and what it means to be a subspace and all the cool stuff we can do with each of these. So if you remember back to recitation, we started out with just talking about what a set was. So we've never really encountered a set in mathematical terms before. And so a set is just a group of things, just in general terms. So we're in a math course. We're going to be dealing with mathematical things. But for instance, this could be a group of anything, right? There's no reason, for instance, it can't be a group of really cute puppies. Yeah, sorry, I just had to get everyone's spirits up just a little bit. But, you know, we're talking about math here. So in general, we'll be talking about sets of like numbers. So it could be 9, pi, negative 7/3 maybe. You could also have functions. So say x, sine of x, and then negative e to the 2x could be a set. They also don't have to have just 3 things. I'm just using that as an example. So you can have like negative 1, 0, 1, 2, and so forth, you know, be the integers that are going on, and just have an infinite set here as well. So a set is just a group of things, okay? It's things that don't necessarily have stuff in common, but could. But we have this notion of a vector space. And what that is it's literally just a more interesting set. So it's a set with special properties. And you know what these properties are because we're doing this as kind of a review. But pretty much with a vector space, you have 3 key components here. So the first is usually denoted with a plus sign. It just means closure under addition. And what does this mean? It means that if I take 2 elements in my set, so let's just call them x and y, they're both in my set S. Then if my set is closed under addition, it means that if I take the 2 of them and add them together, I still stay in my set. I'm not going anywhere. That's what closed under addition means. In the same way, denoted by a little dot here, you have closure under scalar multiplication. And what that means is that you take some element in your set here, so I'm just going to call it x, sorry, and you take another element in some field. In this course, f is going to be just like the real numbers, for instance. It could be complex, but usually just real numbers. And then we say if your set is closed under scalar multiplication, if I take my element that's in my set S and I multiply it by any scalar here, I should remain in S. So there's no going anywhere under this operation either. And finally, you need to have a 0. So that means that whatever your notion of 0 is, based on what your set is comprised of, you have to have that within your set as well. So if we're working with vectors, for instance, you need the vector 0, 0 everywhere in there for you to have a vector space. And we'll see why in a little bit, but this is definitely one of the more important and often overlooked pieces of a vector space. Okay, so we have these special properties here, just as some examples of vector spaces. We have the real numbers. So the number line, for instance, if I look at it, I can pretty much, you know, convince myself that I'm not going anywhere if I add stuff up or multiply. And I know 0 is a real number, so that passes that check. One we often use in Math 240 is polynomials of a certain degree, less than or equal to n. And then one that's generalizing, just the first one, if you extend R to an nth dimensional vector space of real numbers, so like the 3D plane, for instance, sorry, that didn't make sense, R3, all your 3-dimensional vectors form a vector space as well. All right, so these are like the main examples. I'm not going to go through and prove all of them. You can do that yourself if you want. But a lot of questions in Math 240 on finals don't really pop up like this, but you've seen them in homework before, so I want to just go through. It's basically just if you're given a set, you want to show it's a vector space. So for instance, I want to show that my set S, which is given by this notation here. So I have first what my set is comprised of. So I'm going to be working with functions here. This vertical bar means I'm subject to some constraint, and then the constraint follows. So I'm working with functions that satisfy this differential equation here. And I wanted this example because you don't have to solve this differential equation. So, we're through chapter 9. Everyone knows how to solve this partial differential equation here. But what we're not supposed to do is solve it. We're just supposed to show it's a vector space using stuff from chapter 4. All right, so how do we do that? Well, we need to show these three properties here. We need to show addition, scalar multiplication, and zero. So let's start with addition. So what I like to do here is we need to show that for any two arbitrary elements of my set, if I add them together, I stay in my set. So I like to define two arbitrary elements. We're working with functions, so I'm going to call them y1 and y2. And I'm going to just make sure that they're in my set. And if they're in my set, that means that y1 prime plus 3y1 has to give me 0. And y2 prime plus 3y2 also has to give me 0. So that's fine. I've just defined two things to be in my set here. And then if it's closed under addition, that means y1 plus y2 should be in my set. So if they're in my set, then that means that y1 plus y2, the whole thing prime, plus 3y1 plus y2 gives me 0. So it's like I've almost defined this new function here that I'm sending through my differential equation, and I'm just saying it's y1 plus y2. And then we do a lot of trivial stuff over here that I'm sure you hate doing. But what we do is we just break this up. So we see what this left-hand or right-hand side is actually equal to. So I have y1 prime plus y2 prime because differentiation works that way, right? If you have the sum, you can just move it inside. And then we know this distributive property of 3. I don't know if that's the right term, but whatever. This works out here, and then I like to take one more step just to show everyone I know what I'm doing. And I move stuff around so y1 is at the front and y2 is at the back. And the important step here is you need to use these two things you've defined earlier. So we know y1 is in my set. So I have this term here, y1 prime plus 3y1. I know that gives me 0. So I have 0 here. And I have y2 prime plus 3y2 by this gives me 0 equals 0. And again, the whole reason this works is because you've defined them to be in your set, okay? So what you've done then is you've shown that for two arbitrary y1 and y2, that if you add them together, you get 0, which means you stay in your set. So you're good to go there. Scalar multiplication works the same way. We can just use y1 again. So we know that y1 prime plus 3y1 is equal to 0. And then we can take k to be some arbitrary real number. And then I like to write these if statements. If you don't need to, then that's totally fine. If ky1 is an s, then I know that ky1 prime plus 3 times ky1 is equal to 0. So I'm just defining something new and sticking it in here for my differential equation. And then again, I just simplify the right-hand side. So I have k y1 prime plus 3k y1 is equal to 0. And we know by the rules of math that we can factor out this k. And I have y1 prime plus 3y1 is equal to 0. And then again, I have to use this part up here. I know that y1 prime plus 3y1 is equal to 0. So I have k times 0 is equal to 0, and that always works. So this was a mouthful, I know, but this is how you have to go through and show closure under multiplication and addition. Lastly, we have to show the 0 thing is 0 in S. And so this part's a little tricky. What we have to do is we have to see that if 0 in terms of what we're working with actually is in our set. So we're working with functions here. So that means I need to check to see if y is equal to 0 is a solution to this differential equation, okay? So what I do is I stick in 0 for y and make sure it works. So 0 prime is 0 plus 3 times 0, sure indeed. That's not English, fine. Gives me 0 anyway, and I know that 0 is in my vector space. So I have all three of these conditions are met. So in Math 240, I'm good to go. In reality, there's actually 10 of these you have to prove, but we've narrowed it down to the big three that are really the most important ones you need to know how to do. All right, so if you come across a question on an exam that tells you to show this is a vector space, be very careful because you're not going to want to solve this differential equation. Like, we didn't do any solving of that, right? We just did this arbitrary stuff to figure this out. All right, so that's showing something as a vector space. And then we have to talk about subspaces. So subspaces are kind of cool. We're going to deal with them a lot later on in chapter 4. So pretty much what we have here is we have a smaller vector space contained inside a bigger one. So what, in mathematical notation, this means if I have some S that's contained inside V, and V is a vector space. So we say if S is also a vector space, since it's contained in a bigger vector space, we say S is a subspace. So we can have this notion of little smaller vector spaces going on inside of bigger ones. So let's do a quick example here. We know R2 is a vector space. So we can convince ourselves of that a different time if we wish, but we know it is. And so we're interested in seeing if there are some subspaces inside of R2. So consider just the set S is equal to vectors in R2, so that's what I'm working with here. And then I'm giving them the constraint that X has to be equal to Y. All right, so that's my constraint here. What you can do is you can go through and you can prove that this is actually a vector space. So I'll do it really quickly. We have to show closure under addition. So I know that x1, y1 are in S. So that tells me that X has to be equal to Y. I'm going to rewrite it as x1 minus y1 has to give me 0. That's the same thing, right? I'm also going to define x2 and y2 to be in S. And so I have x2 minus y2 gives me 0. And then I want to show that if I add these two things together here, that I end up still in S. So I have x1, y1 plus x2, y2 is in S. This is a big if here. Then I know that x1 plus x2, let me write this out one more time. This is equal to x1 plus x2, y2 plus y1 plus y2 is in S. So if this is an S here, sorry, that was a bit confusing, then I know that x1 plus x2 minus y1 plus y2 has to give me 0. So I'm just giving it this constraint as well. And then, we can do what we did earlier. We can factor this out. And we have x1 minus y1 plus x2 minus y2 is equal to 0. And based off of this constraint that we've given it already, here and here, I know this has to be equal to 0. I know this has to be equal to 0. And so I have 0 plus 0 is always 0. Scalar multiplication works the same way. I'll spare you of that. And then the 0 vector here. What are we working with? Well, we're working with vectors in R2. So I need to make sure that my vector 0, 0 is in my vector space here. And is it? Well, yeah, it's fine. It passes this constraint as well because X does equal Y when both of them are 0. So we're good to go on both of these fronts. So then what we've said is that we've taken this entire vector space R2, we've given it some constraint here, and we still end up with a vector space. So that means we have a subspace And I think it's just best at this point to look at it geometrically. So we have R2 here, this whole vector space. And then we have the line here, x is equal to y. So it's actually a line through the origin because we have 0 involved here. And we have y is equal to x is our line here. And you can see geometrically that this is a subspace, right? So if I start with a vector on my line here, and I add another vector that's on my line, there's no way for me to go but to stay on my line, right? I could be all the way down here if I want. I can be here, but there's nowhere else for me to go. I can't somehow get out here by adding two vectors that are already on that line. Similarly, if I have a vector on my line and then I want to scale it, I can either move it up the line like this, or I can move it down the line like this, but I can't scale it to go out here or down here. So as long as I stay on this line here, I have a vector space. And so all the subspaces in R2 actually are formed by taking lines through the origin here. So there's nothing special about y equals x. It just happens to be an example I took. But all lines through the origin in R2 are going to be vector spaces, and thus subspaces of R2. And this generalizes to higher dimensions as well, where you start having planes through the origin that also work in R3 and stuff like that. But this is just a pretty concrete example for the time being.